Alrighty. So today we released an early access version of the next version of pbrt, the ray tracer that'll be described in the forthcoming 4th edition of the physically based rendering book. This is an early release. It has rough edges and it's not very documented. It will in time be documented through the book, and we're going to kind of focus our documentation efforts there. However, it should be kind of, we hope that it'll be kind of understandable if you know pbrt already. But I did want to make a short video just to kind of walk through a couple of the new things in kind of how the system is structured. So this is more focused on the system structure and in particular how the GPU backend is implemented. I'm not going to talk about the new graphics algorithms. There are a whole bunch of them there. They're described in the README. For those at this point, until the book's done, if you want to understand their implementation, you'll need to kind of refer to both the code and the corresponding paper on that topic. Okay, so first I just want to start with briefly, one of the things I'm excited about is that the system now supports, you can interactively watch the image as it's being rendered using Thomas Mueller's TEV image viewer. So TEV is on GitHub. It's a really nice image viewer. And now pbrt can talk to it over a socket and send the images as being rendered. So just to show that quickly, you pass this display server command line, you pass the IP address of the machine running TEV, and then the image you're going to render. Over to TEV. So this is rendered on my laptop. It takes a few seconds for pbrt to get started. But once rendering begins, you can see the image as it's being rendered. And so that's fun. It's useful. You can zoom in, you can pixel peep, you can do all that sort of thing. It's just kind of helpful as you see your images being rendered. It's lots of fun. Okay, so that's TEV. So if you check out pbrt, it's a pretty similar directory structure to before, with a couple of changes though. So if we go into source, you've got pbrt and the external dependencies like OpenEXR, and then we'll just go into pbrt. So the biggest change, is that, whereas before we had separate source files for each and every shape and camera and filter and all that stuff, now we've collected that. So all the cameras are in cameras.h and cameras.cpp and so forth. There are a couple of different subdirectories now, that should be fairly clear. There's util for kind of lower level utility code, math and 4x4 matrices and data structures and containers and stuff like this. There's command, which has the for each binary executable built in the build. There's the file with the main function lives in command, and then there's base, CPU, and GPU. So let's start with base. So the biggest change, one of the biggest changes, in terms of kind of system organization, is that we've moved away from virtual functions for dynamic dispatch in pbrt. And this was kind of an enabling, a change that enabled the GPU port. So that that has an effect if you're trying to add a new shape or a new light. So I just want to briefly walk through a little bit of that. So what we have now is we have this base directory. For each of the kind of main base classes in the system, shape, light, camera, material, all of those have a header file in base. And this header in base, basically, it does two things. First of all, it defines these handle types. So here we have a shape handle, and all of these handles, and this is kind of the replacement for a shape pointer with virtual functions. So now we have these handles, and they inherit from tagged pointer, and tagged pointer is some kind of C++ template insanity, but that it gives us the engine to do the dynamic dispatch. But you don't have to worry about the implementation of it. But the point is that you need to register each instance of a particular type in this tag pointer template parameter list. So you can see here all of the shapes that pbrt now supports. And by registering them in this way, A, it's able to do dynamic dispatch, and then B, in the GPU path, you'll see we'll be able to kind of do some fancy things where like we iterate over all the types. You know, so we say for each type of sampler, we're going to do something, you know, which is different than like iterating over like the types that are instantiated in the scene or something. So these headers and base define the interface that each implementation of this type has to fulfill. It includes toString. You know, so every shape has to provide an implementation of one of these methods. And this is essentially the same set of methods that pbrt-v4 supported or required from shapes, but there it was through abstract base classes and virtual functions. So here, you don't have the same level of kind of compile time enforcement of that stuff, but you know, hopefully it's pretty straightforward. Okay, so you know, so that's kind of the key, you know, as far as the system structure of the CPU port of pbrt, that's basically the only change. Well, I mean, there's more, but you know, that's kind of the most important change, or that's the only one that's worth really going into here. Next up, I want to say a bunch about the GPU implementation and walk through some of that code. But let me motivate that first. Okay, so I've logged into I'm logged into another machine here. This one has 32 cores. It's one of the Threadrippers with 32 cores and 64 threads. So let's start out by rendering that on that CPU and see what that looks like. So here I'm going to pipe the image to the instance of Tev running on my laptop here. Let's just go clear that out, and now we'll start rendering. And now we'll wait just for the scene to get parsed and stuff. And it's much faster, right? You know, and of course, you know, it's clocked much higher than my laptop, and it's got a lot more cores. You know, and we see this image, you know, chugging along nicely. If we go back, you can see on the command line, it's supposed to render 256 samples per pixel. I just killed the renderer, but you know, we're looking at about, we're going to do math, 165 seconds to render it at 256 samples per pixel. Okay, but let's try doing that on the GPU. So same command line. If you build with GPU support, you still have to do --GPU on the command line to enable it. We'll clear out our old image and render. Now, this is actually looking slower than it is because of network buffering. So that first set of samples was actually done much more quickly than it appeared. And if we go back to the shell, it's actually done. So if we scroll back up, so it's about 12.5 seconds to render that at 256 samples per pixel on the GPU. And to me, that's pretty exciting, you know, because you know, if we go back to the 165 seconds we were trending for the 32 core CPU version, you know, we're 10x faster than you know, a beefy modern CPU. So you know, that's the motivation for the little bit of complexity we're going to go into now for kind of how the GPU backend works. And I should add, you know, that kind of, you know, as I explain all this stuff, you know, if you're working with PBRT, or if you're extending it kind of at the level of graphics and graphics algorithms, you know, if you're adding a new light source or something like that, you know, you shouldn't need to, if you don't want to, you shouldn't really need to worry about how, what I'm about to show you about how the GPU stuff is wired together. You know, so it should just work, you know, if you get the details right, you know, that your new light or whatever will just work in the GPU path. In the same way that, you know, you don't have to worry about the implementation of the bidirectional path tracer, you know, when you're adding a light to pbrt before, right? You know, you just fulfill the interface and then render your scene, and then, you know, it all just works. So should be the same sort of thing for the GPU path. But I think there's some interesting stuff to see in it. So I'm just going to quickly go through some of that. So the big challenge in the GPU version is polymorphism. And pbrt, by design is highly extensible, and there are all sorts of instances, different types of the same thing. And what this means, and on the CPU, it's fine, right? You're rendering a single pixel sample in a thread. If your thread just kind of does whatever it needs to do for the type of light it hit or the type of shape it hit or whatever. But on the GPU, because you have this kind of, groups of threads executing together stuff, polymorphism can have a much bigger effect on performance. So to get good performance on the GPU, you have to address this, and kind of that's how the design of the GPU backend, was informed. The key ideas here are a couple of things. So we have a sequence of kernels. We're doing some chunk of work in the rendering computation, and these kernels are fed by queues. So kind of preceding kernels in the pipeline can queue up work for subsequent kernels, and then each kernel just kind of consumes the work from its queue and operates on it in parallel. And that's like pure data parallel. Elements are processed independently, and that's what we parallelize over. And this is effectively the architecture that was described in the Megakernels Considered Harmful paper, by Simuli and friends. And this is a really great paper. This kind of, if you'd like to understand why the GPU stuff in PBRT is structured, why it is, this beautifully lays out the kind of trade-offs and issues. So definitely check that out. Okay. So these are the main kernels in the system, and we'll walk through some of this code shortly, but just to give a high-level view of how it all works. And it's the classic structure of a path tracer, just decomposed into kernels with queues feeding them. We generate a camera array, for at a pixel for a sample. In this case, we have a separate kernel to generate random samples. Talk about that in a sec. And then, we find the closest hit, and then we queue up into additional kernels based on what happened at that hit. This version of the pipeline does not include subsurface scattering or volumetric scattering, which adds a number of additional kernels that I'm just going to gloss over for now. Most of the work happens, the key stage, the key to the efficiency of it is the sorting stage that happens during intersection. So when a ray surface intersection is found, the work for that is done on a different queue, is put on different queues based on the specific material found. So everything diffuse goes here, and everything, dielectric goes here, and conductors and so on. So what that does is it lines up kind of coherent work, to work on. So we can work on all the diffuse stuff all at once, and that's more coherent than interleaving different material types. And then in this kernel, which we'll look at shortly, basically all the usual stuff happens. We evaluate the textures, we get a BSDF, we choose a light source, we choose a point on the light source, we sample BSDF, queue a shadow ray, and queue an indirect ray, Russian roulette, go back and do it again. So classic path tracer, it's kind of the heart of your regular path tracer. Okay, so let's go look at the code for this. Okay, so this kind of material evaluation stuff I just described is currently in GPU surfscatter.cpp. I should add that all of this stuff will probably shift around in the coming months. So this may be a little stale depending on when you're watching it. Okay, so this material in BSDF so on work happens in this evaluate material in BSDF method of the path integrator. And you'll notice here that it's a templated method. So it's templated on the type of material and then a texture evaluator thing, which I'm not going to go into today. It's just a little wrapper around texture evaluation. But basically, in other code, which we won't look at now, what's happening is that code is looping over all of the types of material in PBRT, via that tag pointer thing we saw before, which allows us to kind of iterate over the types. And then for each type, it's calling this method with that particular material type. So then we get instantiated for diffuse material or whatever. Now, we have this for all queued construct. And what this is it wraps a parallel for loop over one of these queues feeding into a kernel. So each kernel has a queue going in with its own little struct that describes what the work items are in the queue, and then we can do a parallel for over that, and then that takes a description, which we use for printing stats and stuff. It takes a queue to pull work from. And in this case, the eval queue is kind of this multi-queue where it kind of wraps a queue over each type of material. So we have to ask for the queue for our specific material type and a maximum queue size. And then it takes a lambda. And then, these lambdas, the key thing with the lambda is this first argument, is this work item. So, this is a struct that kind of, that holds all of the, the values for a particular work item on the queue. So you're just given the struct, like, hey, here's your input. So then what happens, and then you start doing work. And that is, so kind of from here on out, it's pretty much the same, as the path tracer, on the CPU. And the difference is just that, when you want the shading normal, well, it turns out that's one of the, that's one of the values stored in the work item you're given. You just pull it out of that work item struct. So you're just getting that out of the queue. And then everything else follows similarly. So we do the same bump mapping calculation as before. We use the same bump function to compute the partial derivatives. We get the BSDF. There's a little bit of stuff related to the G buffer that we won't worry about. But then there on out, again, it kind of continues in a very familiar way. We sample the BSDF for indirect lighting. Did we get a sample? If so, then, we path throughput some PDFs, do a little more work, apply Russian roulette, and then we spawn the indirect array. So whereas before we would just be doing a while loop, in the integrator, where we kind of go around again to trace the indirect array. In this case, we're just pushing the indirect array onto the array queue for the next bounce. And then subsequently, eventually the kernels will run to consume that. And I won't walk through all the details for direct lighting, but it's the same idea. And you can check out the code yourself. It's just kind of, same structure as the CPU implementation. I'd like to talk briefly, okay, so there's this header work items.h, and all of the different types of work item are declared there. So like, we have array work item, so that's the state for, the array and array queue to be traced. You get the array and, which pixel it's associated with, and, a little bit of information about the previous intersection to use for MIS if we had a light source. And just kind of the state of array, right? So these are things that just be local variables, in the old, in path integrator. And we have a different type for escaped rays. When a ray doesn't intersect anything, it gets put on a queue. So we can deal with the fact if there's like an environment map that has to be sampled or what have you. So work items.h has all of these, all the declarations of all these work items, or of all the sorts of things that are stored in the queues. Now, a couple things about that. So one thing to note, and again, this is something you don't need to worry about, if you're just kind of writing rendering code. But if you're an expert GPU programmer, you may be wondering about data layout. So here I've just defined these structs, and I've said, and in fact, the kernels are just past these structs. Here are your values, do your work. Just like a shader kind of thing. Now, the optimal layout for these things in memory is structure of arrays layout, where kind of for each pixel, integer pixel index or whatever, instead of having it in regular struct layout, it's better if all the pixel indices for the work queue are contiguous in memory. So that way when a group of threads reads their pixel index, then it's a contiguous read, and that really helps with performance. So structure of arrays layout is a much better way to do this. Now it can get pretty grungy to kind of redeclare all of your structs and to kind of write the logic code to kind of re-swizzle it in memory. And I couldn't find a way of doing that I was super happy with. So I ended up, we have this kind of hacked up structure of arrays compiler called SOAC, which is one of the things that gets built with pbrt. So there's this work items.soa file, and this is kind of C-like but not C. But effectively what this is doing is it's basically a redeclaration of the types with some additional information about, lay these things out flat in memory and stuff like this. And what it does is it parses these kind of, parses a very small, subset of C basically to be able to kind of figure out these types and then automatically generate code to read them and write them in structure of arrays layout. So this is nice because A, it's tedious to write that code. B, it can be error prone, but it also lets us kind of add some syntactic sugar. So if we'll go back to we'll look at camera array generation for a second here. So camera arrays are a little different where, they don't consume from a queue. Like this is where it started, where it all starts, and then it pushes arrays onto a queue. So that starts out with this GPU parallel 4, just parallel 4. But it does all of the usual things to generate a camera array, camera generate array eventually. But then you can see when it's writing out the state, for a particular pixel, the syntax is fairly clean. You might expect this to be written as pixel sample state, pixel index.l. If it was kind of an array of structures layout. So we have the indexing in a slightly funny place, but under the covers, so from the user perspective, this is all you need to do. But under the covers, this is actually transformed into SOA write, an SOA write into an SOA array, for the pixel radiance value and stuff like that. The last thing I wanted to mention, so we do a bunch of we saw with materials that we're kind of sorting over all the material types, and having a separate kernel for each one. And just to show one more example of that, another example is samplers. So, in this case, we don't have to iterate over all the samplers, but what we end up doing is we say like, well, on the CPU side, we say, well, what type of sampler do we have? Oh, it's a Halton sampler, great. And then what we end up doing is then dispatching a specialized kernel based on the sampler type to generate the random samples. And we could do this on the CPU as well. It wouldn't have a lot of benefit there. It would save us, the indirect dispatch. But on the GPU, it's a big win because, we can have this kernel implemented knowing the concrete, we have multiple kernels, one for each sampler type, and we call this one. But it's implemented knowing the concrete type of the sampler. And by doing so, it can just stack allocate it, which in turn allows it to not, live in graphics memory, but it can live in registers on the GPU, which is a lot faster. And that works out nicely. Okay. I'm going to wrap up there. I think that's all the key stuff, and hopefully enough to get folks going and enjoy pbrt-v4. Please send bug reports, suggestions, anything would be fantastic. And I'll wrap up by rendering the landscape scene on the GPU. So this is that scene from Laubwerk, and this is going on the GPU now. Again, we have this lag because it's coming in over the network, but see it renders pretty quickly, and 64 samples we just finished in 11.3 seconds. So that's cool. Okay, all right, thank you.